Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. Determine the maximum shear stress in the thin-walled square tube at point A and at point B in the figure shown. So this load here will have, let's call the axis, let's have action mechanics, a pair of forces equal magnitude is added at this point, and the effect of the original load is unchanged. So we have to cancel 2.5 downward, upward rather, and 2.5 downward. So the reaction at this section here through AB would be upward to counter this downward net downward load. So that will have shear effect at the top surface A because shear stress is maximum at the outer fibers. Zero, sorry, zero shear at the outer fibers, but at the neutral axis there is shear effect. Then at the outer surface, top and bottom, there will be no shear. Then we have bending, call that the x-axis, the z-axis, and the y-axis. Bending in this direction, so to counter it should be in that direction. That's a bending moment. Then these two forces, downward and upward, will be cancelled, and this will constitute a torque in that sense. So to be in equilibrium, the torque should be in that direction. So we will just apply it here. Imagine that this section passes through A and B. So let's consider elements at A. Moment is 2.5 times 0.8 meter, so 2 kilonewton meter, while this torque is 2.5 times 0.6. This torque here, 2.5 times 0.6, 1.5 kilonewton meter. So moment of inertia is pi 160 cubed, so 160 to the fourth over 12 minus 160 minus 2 times thickness, 2 times 5, so 150 by 150. So 150 times 150 cube over 12 is 150 to the fourth over 12. So the moment of inertia with respect to the neutral axis, y, is 12.426 times 10 to the 6 mm to the fourth. So at A, we have tension for bending, and we have torsion. So the area O is the area bounded by median line through this section. The median line would be 160 minus half of thickness, so 160 minus 5, so 155 by 155. The median line, area bounded by median line is 155 by 155, 24,025 mm square. And these are the elements through A and B. For A, it is subjected to bending tension, as shown, sigma normal, and shear, because that's an shear effect uh, due to this torsional effect, because it is an outer surface. At B, this is pure shear, direct shear effect of 2.5 kilonewtons with VQ over IB. There's no normal stress or bending stress because the element through B is on the neutral axis here, And remember that the bending stress about the neutral axis is 0, maximum at the outer fibers. So that's the reason. So Q is 160 by 80, half of 160 is 80, then half of 80 is 40. Then the dimension inside would be 150 by 150. So half is 150, half of 150 is 75, then distance of centroid of area to the neutral axis is half of 75, 37.5. So outer dimension 160, half of 160, 80 times 40, half of 80 is 40, then inner dimensions 150, moment of area about the neutral axis, half of 150 is 75, then half of 75, 37.5. So Q is 90,125 mm square. Then at A, sigma A normal is mc over I. So moment is 2 times 1000 squared to convert it to Newton mm. C is half of 160, 80 mm. Moment of inertia 12.426 times 10 to the 6. So cancel out 1000 squared and 10 to the 6. Sigma A or sigma is 12.876 megapascals. Torsional stress, if you remember, for hollow thin tubes, torque over 2 area OT, that's a shear stress formula, where the torque is 1.5 times 1000 square divided by 2, area O is 24,025, then thickness is 5 mm. So it is 6.243 megapascals. The maximum shear stress at A therefore is sigma over 2, square root of sigma over 2 quantity square plus tau square. So tau max is sigma over 2 quantity square plus shear stress square. Remember the radius of the Mohr circle. Sigma A, for example, sigma AX is 12.8746, while sigma AY or sigma AZ is 0. There are no loads that stretches or compresses the Z and the Y direction. So tau max at A, square root of 12.876 over 2 quantity square plus 6.243 quantity square. So the maximum shear stress at A is 8.968 megapascals. At B, there's no bending stress because that's the neutral axis. There is torsion, which is 6.243 megapascals due to this torque here. And there is direct shear, which is VQ over IB. So at B, we have tau max equals torque over 2 area OT, then plus VQ over IB. So there's no bending stress at B. So tau max is 6.243 plus maximum shear 2,500 newtons. Q is 9125 over moment of inertia. Thickness through the neutral axis is 2 times 5 mm. That's 5, that's another 5. So substituting and computing, it is 8.056 megapascals. So that's it for this problem. The closed cylindrical tank fabricated from 12.7 mm plate is subjected to an internal pressure of 1.65 megapascals. Determine the largest permissible diameter of the tank if the working stresses are 83 megapascals and 33 megapascals for normal, 83 for shear, 33 megapascals. So this is the cylindrical tank subjected to an internal pressure of 1.65 megapascals. So sigma longitudinal PR over 2T. So P times sigma circumferential is PR over T. Or PD over 40, and this is PD over 2T if we use the internal diameter. So let's plot sigma L PR over 2T. Let's assume that its grid is PR over 4T. So this is PR over 2T, sigma L, and therefore sigma C is times 2. So again, assume that this is PR over 4T. So this is PR over 2T, 3/4 PR over T, and this is PR over T. So that's sigma sub C. Therefore, these are the more circles that can be drawn. So this is PR over T. So PR over T minus PR over 2T. So the distance between sigma C and sigma L is also PR over 2T. That's the circle. There is another circle. Let's put it in just one plane. This is the first point plotted. So this is the longitudinal axis. And this is the circumferential axis. And that's the maximum already. So that's PR over 2T also, the diameter of this small circle here, which is identical to this circle. Therefore, the largest circle would be this. And the largest radius is the maximum shear stress. The maximum normal stress is sigma sub C. So since sigma W is greater than 2 times 33, which is only 66, so this is tau absolute, the greatest radius. Sigma W is greater than 2 times 33, so therefore this is smaller, therefore shear stress controls. So if that's the case, sigma tau absolute, which is tau working stress, is PR over 2T. The radius of this largest circle is sigma sub C over 2, or tau absolute, and since sigma sub C is PR over T, divide by 2, so it is PR over 2T. So 33 equals P radius over 2 times 12.7. So R is 508 mm, therefore the internal diameter is double this value, 1058 mm, 1016 mm rather. The cylindrical tank has an external diameter of 500 mm and a wall thickness of 12.5 mm. The tank is pressurized to 1.4 megapascals and carries an axial tensile force of 105 kilonewtons. Determine the maximum normal and shear stresses in the wall of the tank. So that's longitudinal direction, then circumferential direction around the surface of this cylindrical tank. So longitudinally, it is subjected to longitudinal pressure, PR, longitudinal stress, which is PR over 2T, or PD over 4T. Then aside from that, there is also an axial tensile load, 105 kilonewtons divided by area of the ring, annular ring. So longitudinally, we have PR over 2T plus P over pi R outer square minus R inner square, where R outer is 500 over 2, 250 mm, while R inner is 250 minus the thickness 12.5, so 237.5. R outer 250, R inner 237.5 mm. Substitute sigma longitudinal is 1.4 times 237.5 over 2 times 12.5 plus 105,000 newtons over pi quantity 250 square minus 237.5 square. So computing sigma longitudinal is equal to 18.785 megapascals, while sigma circumferential is PR over T. So P is 1.4, R is 237.5 over 12.5. So sigma sub C is 26.6 megapascals. So the maximum normal stress, therefore, let's have the Mohr circle construction. Let's plot first sigma L, which is 18.785, assuming its grid is 5 megapascals. So that's approximately 18.785. Then 26 would be somewhere here, 26.6. And this is the Mohr circle. This is the first point plotted, so this is the longitudinal axis. Sigma max therefore is 26.6, the farthest value from the shear stress axis. So this is the longitudinal axis and this is the circumferential axis. Then another circle in one set of plane, and this is the biggest circle. And the radius of this biggest imaginary circle is tau absolute. So tau absolute, therefore, 2 times tau absolute is the diameter, and it is equated to 26.6. So tau absolute is half of 26.6, so it is 13.30 megapascals.